Okay, welcome back to part 2 of class 2. And what we're going to do now is go through a little bit more material today. And let's go and get to it. All right, so programming. So we basically know how the computer works. We know that it has a memory, it's got a processor. The processor only does simple instructions. The data for those instructions comes from memory. The instructions themselves come from memory, but the CPU only carries out simple instructions. And if you look at those instructions, there are things like move. And the way these instructions work, in this case, the way I have it labeled here, is this is going to be move to, and then after the comma is from. So again, kind of like mailboxes in the postal system, you say, the instruction says, take this from the value that's in address 10, whatever is in address 10, move it into register A inside the processor. Now here it says take the number 1 and add it to register A inside the processor, performing an add instruction. And then take that result and take what's in A and move it into register 11, or address 11, I mean. So move register A to address 11. So that simple kind of low-level, one thing at a time set of operations is the way that computers work. And all it has is a collection of very simplistic operations. It doesn't know what it's doing. It doesn't think about it. There's no thinking. It's just there's a machine that when it gets this instruction, it does that. And these instructions themselves aren't even written out as MOV ADD. They're written out as, they're stored in memory as just a number that is kind of an encoded version of when the CPU gets this pattern of bits, it causes it to activate the part of the machine that does move something from an address into register A and so forth. So very simplistic. Now, we could program using those low-level instructions if we wanted to. That's the kind of native language of the CPU, is we put those patterns of bits in there that represent those instructions, and it does whatever we tell it to at that low level. But for humans, that can be a tedious way to program and a difficult way to program. And why is that? As well, we'd have to know which address is storing what data, which address is connected to what kind of device. We'd have to know all of the CPU instructions and what codes go with them, how to use them. We'd have to know what numbers or patterns of bits go with what characters and which ones go with what instructions. And it's going to take a whole lot of those really simple instructions to do something complex. So we're not going to program in this class using those CPU instructions, even though that's kind of the lowest level of system programming you can do. We're going to do that in a slightly easier way in this class. And we're going to use a high-level programming language in this class. And so the question is, well, what is a high-level programming language? Everybody in this class should have programmed in something before, so none of this should be new. So examples would be like Java, C and C++, JavaScript, Pascal, Fortran, Perl, Ruby, C#, Rust, Python, Lisp, Visual Basic. I could sit here all day listing different languages, Prolog, Go, NIM. There's just tons and tons of programming languages. So what are they and how do they work? So programming language is really just a special program that translates source code that we write into the actions that the CPU needs to actually take that embody the things that we put in the source code. So for example, this code over here that we wrote, this printf hello, printf world, we would feed that into one of these special programs, and it would either carry out those actions for us or save them off in a file, a machine code file that then can be loaded and executed later. Now, notice that allows us to focus to write our code in something a little bit higher level and a little more understandable. Like I could show this to somebody who never did programming before, and they might not know like the weird curly braces or what void means, but they're definitely going to say, what do you think this does? They might say, well, printf hello, that probably prints out hello maybe. This should just say printf there too. There's a typo there. It should say printf world. And actually, I don't like to leave those things, so let me fix that real quick. So the online version is good. Okay. Now, so essentially, we're going to use one of these special programs that does that. And that's why there's so many different programming languages, because that's just a program. So somebody could write a new programming language. In fact, when you take the compiler design class later on in the semester, you're going to write your own one of these programs that converts from source code into the CPU actions. You'll write that yourself later on in your academic career. Okay, now we said there were two versions of that. There are compiled languages and interpreted languages. A compiler is one of those special programs that translates from source code into the low-level instructions for the CPU to execute, and it does it all as once and saves them off in a new file, an executable file. And that's kind of like translating a book. You say, here's a book in this language, convert it to a different language. And so in order to do that, you would go through kind of one sentence at a time, write down the results, save that off, and now you have that book in the new language. Except in our case, that's going to be translating from the source code of the language we're going to use, which is going to be C language. That's going to be translating that into the machine code specific for the processor, just like we had in our picture on this. We're going to be writing our code, and it's going to translate it into these instructions for us. All right, the second type of program is an interpreter, which if you've used Python or JavaScript or something like that before, you're probably used to that. But the only difference there is rather than translating it all at once and saving it off in a new file, it'll translate it one line at a time and make the CPU take those actions right then. So the idea behind the difference between these, it's really the same process. It's just when does it actually make the CPU do something. So that's more like a language translator at the UN, where they have on their headset and they're listening to somebody talking in another language and they're speaking in that other language. And so that's like translating on the fly rather than one line at a time. So interpreted languages would be like Lisp, Python, Ruby, where compiled languages would be something more like C and C++ or Fortran or Pascal. And there's some that are kind of sit partway between the two, like Java compiles, but it compiles not directly to the CPU. It compiles to its own kind of special bytecode that then runs on another interpreter program. So it's kind of like a hybrid with a language like Java. But we're going to be using C language, which is a compiled language. And a couple quick things about C here that I've just put some bullet points down for. First thing, C has been around since 1972. It was created originally by Dennis Ritchie, working at AT&T Bell Labs. And C language, the reason we're using it in this class, is C language was specifically designed for systems programming. That's what it was created to do. And this is a systems programming class, so that's the language we're going to use in here. And it specifically was designed for programming operating systems, and more specifically, it was designed for and created to write Unix in a high-level programming language. So it was designed to give control over the CPU's instruction set. It was designed to give control over memory and how you access memory. So it was designed to be powerful at the machine, kind of bare to metal machine level of control and power that you need to write an operating system. But it was also designed to be portable and readable and maintainable. And like I said, it is a compiled language. So it compiles your source code into the native code of the processor itself. Okay. The whole idea of any programming language is to bridge the gap between what you want the computer to do and what the computer needs to do to make it happen. So a lot of languages are pretty good at that kind of thing. Like Python's a good language, Java's a good language, but they essentially, those languages though, like Java, like Python, like JavaScript, they don't give you enough control to write something like an operating system or to create something that would classify as systems programming. Because systems programming, remember, the whole idea is we want to control exactly what's going on in this machine. Meaning we might want to go to some space in memory that's connected to some piece of hardware and directly access that in some way. Or we might want to cause the CPU to perform very specific operations on the data that's stored in memory or in its registers. And most other languages, like let's take Python for example, they just can't do that. It runs on its own interpreter, it runs on, or in Java's case, it runs on a virtual machine. It doesn't give us access to direct control of the hardware. And so that's where C language really shines, is that's what it was created to do. It was created to write the Unix operating system. And it was created to do systems programming. It's the tool of choice for doing those kinds of things. So let's take a quick look at the timeline of C language. So this has a lot of words on here, but I'm going to add a little bit of detail or a little color to this as I go through the list. So the first thing here is in 1972, Dennis Ritchie was working at AT&T Bell Labs. And Bell Labs is kind of a research arm of AT&T, where AT&T had a lot of money and they sponsored a lot of projects that they thought would be cutting edge or that could give them a ability to stay on kind of the forefront of technology. And one of those things they were doing is they had this computing group that Dennis Ritchie was a part of, and they realized fairly early on that computers are going to play an important role in telecommunication systems. So let's have a group that works on writing software and operating systems for computer systems. And so Dennis Ritchie was part of that group, and they had created this operating systems project that they called Multics. And the idea there was, prior to their creation of that operating systems were things that came with the computer you bought, and they were kind of created by the company that released the computer. They were all written in the kind of native machine code of the computer hardware and written by the manufacturers of the computer system. That meant that they weren't really compatible with each other. So they created this Multics project, and the idea was Multics stood for multi-computer system operating system. And so they wanted to create an operating system you could use on a range of computer systems. Well, the problem with the Multics project was that they basically tried to design and build this operating system that was the be-all and end-all of everything you'd ever want in an operating system on any piece of hardware that you could put it on. And there were two problems with that. The first problem with that was that it was such a large project, so ambitious that they never really got a working version of it that would work on a range of different computer systems. The second problem they realized with it was that it's a really large project that was also written in machine code, and if you wanted to port it to another machine, you had to rewrite the whole thing basically. So every time you wanted to put it on a new system, you'd have to completely rewrite it. And so they learned from that project two things. The first thing was, it's better to make an operating system that's smaller and simpler, and we really need a high-level language to program this in to make it portable. Otherwise, you'd have to rewrite it every time you wanted to put it on a new system. And so what they did is, after the Multics project kind of was deemed impossible to complete, Dennis Ritchie and a few of the other researchers there said, well, let's take a different approach to this. Let's make this thing called Unix, which is, instead of Multics, it's kind of a play on words in two ways. One is they thought of it as Multics is many, Unix is one, uni is one, but it also is a play on words with the word eunuch, which means kind of castrated. So they thought of it as, let's take this giant Multics project and then trim it down to the bare essentials. And they thought of that as, well, we're kind of castrating it into this smaller, simpler thing. But as part of that project, in 1972, there was this other part that they needed to write this in a high-level language to make it really portable to multiple systems easily. And there's no programming language that existed that was capable of that. So Dennis Ritchie decided, well, we'll create our own language and write the operating system in that. So they created the language in 72. The next year, in 1973, after they worked out some kinks with C language itself, they realized it was fast, it was flexible, it was powerful, and allowed them performance that was comparable to anything that you could do in the machine code itself. Hold on, I gotta move a cat out of the way. And so they decided, hey, this thing is ready for us to write the operating system in, and they rewrote the entirety of Unix in a high-level language, C language, that they had created specifically to write operating systems in. And So now that was the first operating system that was written in a high-level programming language, and it was the first high-level programming language capable of writing an operating system in because of the powerful features that they added to it. Now, there's an interesting twist that happened in this saga that in the late 70s, notice that they had from 73 to somewhere around 77, 78, they actually encountered, I wouldn't call it a problem because they knew this was the case. They were researchers just working on this stuff. But now they had this working operating system that was written in a high-level programming language, and it was just as fast and powerful as an operating system written in assembly language that was harder to update, harder to change. And like, we have a really cool piece of technology here. We want to share this with other people. But the problem was that AT&T, which at the time hadn't been broken up yet, it was like this large company that provided telephone service for pretty much everybody in the entire country, but they were under a antitrust consent decree with the US government that prevented them from competing in the computer software and computer hardware marketplaces. And the reason for that was that they were such a big company that it was thought that if they were allowed to create their own computers, their own software, that they could use their telecommunications monopoly to kind of force other competitors out. So they were just not allowed to compete. So Dennis Ritchie talked to the people at Bell Labs, and he said, well, what do you want us to do with this thing that we created? And they said, well, we can't sell it. We can't make money off it. So we don't really care what you do with it. And so what Dennis Ritchie and Ken Thompson decided to do with Unix was they decided to release it for free. So they actually made it freely available under this kind of free license. And they released along with it the source code, which was written in C language. And then they also released the compiler and the source code to the compiler. And so what they had was this freely available new operating system that universities could use, computer science departments could use, engineering departments could use, all over the country. And all you had to do was take and implement the compiler on your system, and then you could compile it, and you'd have this new operating system that ran on that. So essentially, as C language and as they released that and sent it around to people for free, there's actually this cool story where Ken Thompson himself, they said, you send us the money for the media, the tapes or discs or whatever distribution method it was, and we'll send it to you for free. So he would make copies of it, send them out, and he put a little note on there that said love, Ken, along with those as they distribute it. But it was all completely free, so nothing that poor graduate students and computer science students love more than free stuff, especially when it's an operating system that comes with a source code, so you can change it and modify it and do whatever you want with it and port it to whatever computers you have lying around. And so that spread around the country. Unix spread around the country, and C language, because Unix was written in it, spread around with it. So that kind of 1978 version that became very widespread of C language became known as the K and R standard. And the R stands for Ritchie. K stands for another computer scientist, which is Brian Kernighan, who worked with Dennis Ritchie. But essentially that compiler and Unix itself became really widespread at all these universities. When they graduated, they went into business. They kind of took Unix with them. And then it became, so C language kind of spread with it in kind of a viral fashion. There was no internet in a lot of places back then, at least it was not widespread. But it's kind of spread virally across the academia kind of use space, and then into industrial and research and other military and other use spaces after that. So Unix and C kind of spread together. Now, fast forward just a little bit to 1983. As people started using that and modifying it, it kind of became a problem because as people ported it to their own systems and changed the language around a little bit, it kind of became where there were different versions of C language and slightly different versions of Unix built on those different versions of C language. So James Brody of Motorola, same Motorola that still makes cell phones and used to make chips and all kinds of other things. Way back in the day, they made radios. James Brody applied for an ANSI standard for C, saying we need to standardize this so a program that somebody writes in C on a digital equipment computer will run on data general thing. So rather than having to make changes to the source code, let's standardize it. And in 1989, the ANSI standard was ratified as C89 or ISO C90, which was shortly after that. And ANSI is the American National Standards Institute. They just keep track of standards for things. They made a standard for C language, and that became the official standard in C89. Now, fast forward to today, there have been several updates to the standard along the way, starting with the original K&R standard, which really that wasn't a standard that had a standards group. That was just Brian Kiernan and Dennis Ritchie. Hold on, there's a cat creating strange noises. Stop that. All right, sorry. I don't know if you could hear that. The microphone is picking that up. The cat is like scratching on the side of the conference table for no reason. But anyway, the K&R standard was that Kiernan and Ritchie wrote a book that was like, here's how C language works. That became the standard for a while. That was replaced by the C89 standard, and then the C90 standard is kind of the same as C89. But then fast forward, there's this one in 1995, there's one in 1999, and the most recent one, C11, was adopted in 2011. And they've added some additional features and some additional things. Most of what we're going to talk about in this class is going to be kind of focused on C89, but I will point out some additional features that were added in these later versions as we go through. Some places I'll point out this works in C99, and later this works in C89. But if you wanted to target a kind of least common denominator system, it'll compile on anything that has a C compiler. Probably C89 is a good choice for that. Okay, now a couple additional things here. Since C was designed to be a systems programming language, it was by nature designed to be powerful and used as a replacement for coding directly on the hardware in machine code or assembly language. And that's where it gets a lot of its power from. So it gives you direct control over the CPU, direct control over memory in ways that other languages cannot do that. For example, you can do things in C that you absolutely cannot do in a language like Java or Python. And that's why it was created, because it was created to create operating systems as an operating systems authoring language. And you just couldn't write an operating system in Python because it can't access the hardware or the memory in the ways that you would need it to. Okay, now that brings us to this, the nature of C language itself. And there's an ideology associated with C. And there's a quote in one of the documents that Dennis Ritchie released, where their concept when they created C language was trust the programmer. In other words, if somebody's writing an operating system or doing systems programming for an operating system, the idea is they're probably pretty smart and they should know what they're doing. So let's trust them to do what they're doing. And so C language has this reputation of being kind of cryptic and dangerous and promoting bad programming habits. But really, it's kind of not undeserved, but it's also a little bit unfair as well, because what C gives programmers is power and liberty to do things, including things that are dangerous or stupid or bad. And it also gives you this power of expression that can be used in cryptic ways, or you could write good code if you're a good programmer. So again, it was designed for doing systems programming and writing operating systems. And to do that, you need to have low-level ability to access low-level things in the processor and in memory. And those, just by its nature, it giving you the liberty to do those things makes it so that we have to be a little bit careful. So in this class, we're going to focus on writing good programs. I'm going to try to point out cases where here's a case where you could do this in the bad way, or here's a naive way of approaching this that's dangerous. Here's a way of doing it where it's safe. So I'm going to try to point those things out as we go through the course. So what do we mean by a good program? Well, a good program in this class means that it works and it's safe. So if we have a program that works, it does what it's supposed to do, it doesn't crash, it doesn't have other bugs in it that cause problems, then that's considered good. But that's not good enough. You could write a program that works and isn't safe. That would be bad. You could write a program that is safe but doesn't do what it's supposed to do. That's not a good program. You could also make a program that works and is safe but is really hard to read and hard to maintain and hard to update. And so we're going to focus on doing that too. We want to create programs that are kind of structured nicely, organized well, and not just a big mess of garbage that's impossible to read or understand or maintain or troubleshoot. So we want to make sure we're doing that. So C language is powerful and it trusts that the programmer knows what they're doing. So it can be dangerous, but it can also be safe if we use it carefully and properly. And that's what we're going to focus on in this class. Okay, C language performance. Well-written C code will be faster than code in any other high-level language. And that's a statement that I stand behind, that if you have a well-written C program, it's always going to be faster than a well-written Java program or a well-written Python program. And the reason for that is because of that low-level control it gives you over the hardware. It's almost like you're programming directly on the hardware itself. Now, you can certainly write crappy programs in C that are really inefficient and badly written. And you can write programs that are dangerous in C that crash and don't do what they're supposed to do. We're going to try to avoid that in this class. Now, a couple of things here. Every operating system that you've encountered is probably written mostly in C. There's some movement where parts of operating systems are moving into C++, which is a object-oriented extension of C. And there's some parts of operating systems are now in other languages like Python, things like that. But primarily, the operating system itself, the kernel of those operating systems, is all written in C. So for example, Unix/Linux, probably 99.9% of that is C, and all of the kernel code is C. Windows is C. OS X and Mac is C. Android is C. Mac OS, C. So all of those operating systems are all completely or mostly written in C. And then one other thing that's interesting is other programming languages. The tools for those, like the Python interpreter that you run when you're using the standard Python distribution on Windows, that interpreter is written in C. You can actually download the source code for the Python interpreter that's written in C and look at it. It's just a C program. The Java virtual machine, the Java compiler, subcomponents of that are written in C. The Microsoft's .NET Common Language Runtime, the CLR, is written in C. And so C is kind of this mother of a lot of other programming language and a lot of other systems. If you are like using a smartphone, C language runs on that. If you're using a embedded system of some sort, for example, there's a work project that I have here that's there's a little GPS module on here that's programmed in C internally. And so C, it really shines in that low-level embedded systems world. It also, like Arduinos, if you have programmed an Arduino, that's C++ and C that underpins that kind of system. Okay, so really it's pretty much everywhere. Now, the other thing is, despite the almost 50-year history of C, it's still really widely used and still really popular. So if you look at the TIOBE index for 2020, this is kind of a place that tracks programming language popularity. You notice #1 on the list in August of 2020, C language. Still, after 50 years, even though we have all these other programming languages, C is still at the top of that TIOBE index. And you can look, this tracks this is a chart of them starting in 2001 or so. But you'll notice that C language, which is this kind of bluish colored one here, has remained very popular, had a little dip here, but then came back. But it's been consistently at the top of or near the top of the index. And you'll notice some other language like Java has actually lost some popularity. C is about where it was from about 20 years ago. And really, it's about where it was from 30 years ago and before. And you'll notice that languages like Python have made some inroads and have come up some, but it coming up has not diminished C. It's still, they're kind of up there together. Other things have kind of dropped off a lot, like PHP has dropped off a lot. And then there's some new languages like R that have made inroads. But you'll notice C language consistently at the top. One other thing is if you look at the IEEE rankings of programming languages, you'll notice C language is in the number 3 position. If you combine that with C and C++, or you combine C and C++ over here, which are closely related. C++ is a superset of C. So if we were to combine those, so in other words, we come over here and combine the C and C++ together, this one and that one, it would be well above any other programming language that's available. So the C and C++, really good things to learn, marketable skill, help you get a job, very useful for a lot of different things, from embedded systems to application programming on the desktop to mobile programming for mobile platforms. And one of the things, other things that I should probably emphasize here is, remember I said that C was really fast and really powerful. There's also, if you're using, if you're making a system that needs to have performance, I'm looking at you, people who are doing embedded systems, or I'm looking at you, people who are writing games, then a lot of times it can help to optimize your code by putting parts of it into C libraries and then calling those from whatever other language you're using. For example, if you're using Java and you use their Java 3D library, or you make OpenGL calls from Java, guess what those libraries are written in and compiled in? C, maybe some C++. Okay, so we're pretty much at the end. What we're going to do next class is we're going to dig into learning C language. Hopefully today provided a little bit of motivation of why we're using C. Powerful, fast, designed for systems programming, but also really good for you to know, really marketable skill, and being the foundation of all those other programming languages, it can be really helpful to know how to write code in it. Now, some things in C language are going to be very familiar, like variables, functions, making calls to those functions, doing things like making decisions with if statements and loops with while and for structures. But some things are also going to be quite a bit different, especially the way that C handles things like arrays and memory accesses and pointers, which are essentially addresses to things in memory. Some of that's going to be a little bit different and a little bit lower level than you're used to. And what my goal for this class is for you to become comfortable writing well-written, safe C language programs. And then also we're going to add some C++ toward the end of the semester. So I want you to also be able to distinguish between this is C and this is C++. And over the years, I've written, probably a million lines of C code for various things. And it's a little bit different way of thinking about programming in some ways, but it also, it can be a little more satisfying in some ways because you know exactly, in most cases, what the processor is doing and how it's accessing things in memory and how things are stored. Where a language like, I don't know, let's say Python or Java, where you just say create an object instance, and you don't really know where that is in memory or what it's doing or how it's doing that, and you, which is also kind of frees you up from having to worry about that, but you don't have control over it. You're at the mercy of the virtual machine or at the mercy of the interpreter. In this, we're going to be writing code that compiles directly to the hardware. And that is going to be, that can be pretty cool because if something isn't working, it's your fault. There's no, in most cases, there's no library to blame. There's no outside forces. It's you writing code that goes directly to what the processor does. And if the processor isn't doing it right, you probably did something wrong somewhere. There are cases where the compiler can have bugs in it, but unlikely you'll encounter those. Okay, so let's stop there. That's it for today. Everybody stay safe. Again, as a reminder, there may be a quiz. for next class. So everybody stay safe, and I'll see you next time.